Section 4.3 covers the topic of direct proof. So let's talk about the basic setup of a direct proof. A direct proof is going to be a proof technique that's going to allow us to prove conditional statements. So statements of the form if P then Q. So maybe if we have a statement which is written using quantifiers, we could rewrite that statement as a conditional, and then we could use a direct proof for it. But we do have to have this if P then Q. And the basic setup that I like to think about is assume or suppose P, show Q. Right, so when I'm doing the proof, I'm going to start with either suppose or assume. You can use either word. Whatever P is, blah, blah, blah. So basically in here, we're going to use some definitions, maybe do some basic algebra, use some more definitions, etc. And at the end, we're going to be able to conclude whatever Q that statement is, and then we'll be done. So we often use this box, so you can get this in tech using /black square, and that little box indicates that we're done our proof. Can also maybe see people use QED, so stands for quo error demonstrata, which means like as it has been shown. I like to end my proofs with a smiley face. That is less conventional, but acceptable in my classes. So why are we actually doing this? Why do we suppose P and then just show Q? If we think back to our truth table for an implication, if we have our P and then our Q, and then our P implies Q, we know that when P is true, we need Q to be true in order for the statement to be true. Because if P is true and Q is false, then my statement is false. But if P is false, it doesn't matter what Q does. That's always going to be true. So the only thing we need to check is that whenever P is true, I also need Q to be true in order for my statement to be true. Because when P is false, it doesn't really matter what happens to Q. I'm always going to get true. So we just check when P is Q is true. Is Q also true? If yes, if whenever P is true, Q is true, then P implies Q is true. So all we need to do is just suppose or assume that F and show the P. Assume the F, show the P. All right, so let's go ahead and do it. So I've got a pretty basic statement to start off here. It says if X is odd, then X squared is odd. So I'm going to put first proof, where you could write out the whole word so we know we're starting. And then we'll suppose or assume the if. So assume X is odd. I'm going to explicitly say that it's an odd integer. And now what we need to try to get to here is that some stuff in the middle, therefore X squared is odd. So usually what we do first, we say, okay, I'm assuming X is odd. So what I should do is write out what the definition means for it to be odd. So we'll say then, because it's odd, X can be written as X equals 2n plus 1, where n is an integer. That's what it means for X to be odd. It can be written as 2n plus 1 for some integer n. Now I want to be able to say something about X squared. So let's go ahead and say what X squared is going to be. So X squared is equal to 2n plus 1 squared. We use a nice display equation here. So I'm going to line up those equal signs with each other. And then I can multiply this out. 4n squared plus 4n plus 1. And now I know that I'm trying to get that this x squared is odd. So if I sort of work backwards, what would allow me to show that x squared is odd? I would need to say that x squared is equal to 2 times something plus 1, where that something is an integer. So why don't I go ahead here and pull out a 2, and then we'll see what's left. 2n squared plus 2n plus 1. So I can say let this m equal 2n squared plus 2n. Since n is an integer, m is an integer, because the integers are closed under addition and multiplication. So if I start with an integer, I multiply it by 2, I square it, I multiply that by 2, I add them together, I still get an integer. So then this x squared is equal to 2 times some m plus 1, where m is in z. Therefore, we conclude that that x squared is odd. So this is the basic format of our sort of simple proofs we're going to take. All right, we assumed the if, definitions, algebra, definitions, got to my then, so now I'm done. So I can draw my little ending box, or happy face, QED, whatever you prefer. Okay, so let's go ahead and work through one more proof here. So I'm going to do some scratch work for this one. I'm not going to just try to write it out and make the statements meet in the middle. So I know I have a, b, and c that are integers, and I want to prove if a divides b and b divides c, then a divides c. That's my goal here. So I'm going to assume that a divides b and b divides c. So I'm going to go ahead and just automatically, whenever I have these types of things that I'm assuming in my proof, I always like to unpack that into a definition. So this says that b is equal to some n times a, where n is in z, and c is equal to, I'm going to pick a new letter, m times b, where m is in z. So I just assumed my thing, and I went ahead and I unpacked those definitions right away. Now, as I'm doing my scratch work, I also want to think about what I want to show. But it's really important when I start writing things down that I'm clear about what things I know for sure and what things I don't know. So I want to show that a divides c, which means that c is equal to some constant times a, where that constant is an integer. So whenever I write something down that I haven't shown yet, but I want to show, I'm going to stick that in a box to remind myself that I'm not actually there yet, because I can't use that in my proof. It's just what I'm hoping to end up at. Okay, so now we'll go back to our assumptions here. I'm trying to figure out what c is equal to. So I notice I have a c here. So c is equal to that m times b, but I want it to be something times a, but b is equal to n times a, so that's equal to, b is equal to n times a, so I put that in, so I get m times n times a, and now I can just write it as m times n times a, and that looks good. So I got my c is equal to some integer times a, so I should be ready to go. So now we can go ahead and put this all in words. So we'll say proof. Suppose the if a divides b and b divides c. I can't do anything with my then yet. I just want to remember that's where I'm heading. Sometimes people do write what they want to show next, but we don't have to, so I'm going to leave that out. So suppose a divides b and b divides z. Then, by definition, we know that b must equal n times a, where n is an integer, and C must equal some m times b, where m is an integer. Therefore, now I'm going to be doing sort of a long calculation here, so then I might want to center that when I'm typing it. Write C is equal to m times b, which is equal to m times n times a, which is equal to m times n times a. So I'm showing my nice calculation in the center there. All my equal signs are aligned. So then we can conclude. So since I need this guy to be an integer, C can be written as an integer. Maybe we should then define the k before we write it. So we'll say since m times n is an integer, let k equal m times n. Then C is equal to k times a, where k is an integer. Thus, we can get that a divides c, which is what we wanted to show. So I'll say as needed, and then I'll draw my little end of proof box. All right, so let's go back through again. So we said, suppose A divides B and B divides C. So that was the if, assumed the if. Then we unpacked those definitions of divide here. Again, in this proof, we had to do some algebra in the middle to use those definitions to get to the last definition. I concluded the thing I wanted to do. I ended with my then, and then I could get my conclusion. I ended with a nice little box here. All right, so now it's your turn. So I want you to see if you can prove the following statement. If x is an even integer, then x squared minus 6x plus 5 is odd. So try to go through the same process and see if you can come up with a proof for this. Here I've presented a proposition and proof from the book, and I want us to go ahead and read through that and kind of see what techniques they're using and how they're doing this. So what are they trying to prove here? We have three integers, so we've got a, b, and c. So natural numbers, so positive integers. And I want to show that if you have three positive integers, then the least common multiple of c times a and c times b is just c times the least common multiple of a and b. So whenever we're doing proofs like this, it's really helpful to first convince ourselves that the statement is true. So I'm going to go ahead and just look at a few examples first. So maybe I can let a equal 3, b equal, I'm going to be thinking about the LCM. So maybe I'll have that be like, let's not have a, b. Well, okay, we'll start with 3 and 5. And then c can be, say, 2. Okay, so this tells us that the LCM of 6 and 10 should equal the LCM of 3 and 5 times by that 2, where I get to put the 2 in front like they had it. So let's think about that. It's the least common multiple of 6 and 10. I know that 30 is a common multiple of both of them, right? That's going to be the least common of multiples if you just think about all the multiples. You could also do a prime factorization. 6 is 2 and 3. 10 is 5 and 2. And when I'm looking for the least common multiple, I've got to take one of each of those prime numbers that appears. So I'm going to get 30. Over here, the least common multiple of 3 and 5, they have nothing in common, so their least common multiple is a product, so that's 15 times that 2, that's C. So in this case, it did actually work. Okay, so we can kind of convince ourselves that this at least worked in one case. Obviously, that's not a proof, because the proof doesn't say just for one case, A, B, and C. It says for every single one of them, right? For whenever we have variables, we really have that implied for all up front. Okay, so how do we actually go through this proof? So let's go back here. It says assume that they're all integers. Okay, assume the if, good. Now, we want to say something about this LCM. So I'm just going to call that M. And I'll call N C times that LCM. So they're just naming these two terms that we want to refer to. And we're trying to show that they're equal. So next they tell us exactly what they're going to do. We will show that these two things are equal. That's always good to do. And then they're going to turn to definitions. So by definition, LCM is a positive multiple of both A and B. So that least common multiple has to equal a multiple of A and a multiple of B. So it has to be some x times A and some x times B. So they're saying, okay, a least common multiple is a multiple. From there, because we know that that least common multiple is a multiple, we can see that C times that least common multiple is equal to C times AX is equal to C times BY. All right, so just sort of unpacking this. So they said the LCM is a multiple. So then we know that that LCM of A and B is equal to A times X and also equal to B times X. It's a multiple of both. So then N, which was equal to the C times that LCM, has to be equal to C times AX and has to be equal to C times BY. Now they're switching over and focusing on the M instead. M is the LCM of C times A and C times B, and it's the smallest possible of those multiples. Right, so here I have a C times A and I have a C times B. So this is a multiple of both CA and CB, but M is the smallest multiple, so I know that M has to be less than or equal to N. So that's what they have there, that M is less than or equal to N. Now they're going to sort of do the same thing, but analyze it from the different side. So now they say, on the other hand, to indicate that they're going to do a sort of analysis, alternative analysis, we say M is the least common multiple of CA and CB. So it has to be a multiple of CA and CB. So M is a multiple of CA and also a multiple of CB. They're using X and Y again here, but they're different than the X and Y's above. There's still some integers. So then they're saying that 1 over C times N is equal to AX times BY. So if I divide by C, M over C is equal to AX is equal to BY. Therefore, the least common multiple must be less than this number, because this number here is also a multiple of both. Right, this is an integer, and this is an integer. So this also must be an integer because it's equal to them. So therefore, I know that the least common multiple of A and B is smaller than another multiple of A and B, which is M over C. So I get that multiplying through, C times LCM of A and B is less than or equal to M. But now we have both M is less than or equal to M, and N is less than or equal to M. So if both of those things are true, the only thing that can be true is that they're equal. Right, so this is a different type of proof than the ones we've seen before. We are using this technique, which we'll see sometimes throughout this class, when I want to try to prove two things are equal to each other. I first show that one has to be less than or equal to the second, and then the second also has to be less than or equal to the first, and the only way they can both be true is if they're equal. So I encourage you to take some time, reread through this proof, and see if you can kind of make some sense of exactly what they're doing. Okay, for practice, once you've had some time to analyze that last one, I want you to go ahead and analyze this proof. So kind of just read through, see what they're doing at each step, see if there's any steps that seem confusing to you, any steps that are unclear that can be explained better, and we'll talk about that in class. And finally, we're going to actually use that previous proposition to help us prove this one, and we'll work together in that proof when we're in class. So I encourage you to kind of read through this, see if you can come up with some ideas of how you would do it.